Thank you for organizing that conference. It's a pity we can't be in Paris or in Marseille all together. I always enjoyed it a lot. So I hope that's going to happen again next year. So Louis asked me to have a couple of thoughts on theory as a start and to include the Higgs self-coupling. That's what I'm going to do. But as a theorist, before anything else, let me share some thoughts that I had recently discussing stuff. And it came up with this measurement that you saw here on the right-hand side, which is the show-off result, but for instance, by Atlas. CMS clearly has similar plots, and it lists many processes with vastly different rates and how they can be predicted, and they can be measured with extremely high precision. And it's a great success for the LHC, and all of this is predicted by theory. So this is great, except that when I thought about it, why I about what I expect from the LHC and also from Higgs physics in particular is quite useless. So after offending all of Atlas and CMS, let me explain why. Because I think the fundamental questions that we still have to do with particle physics, and that makes us say particle physics as not nuclear physics or not condensed matter, is because we like the physics questions. They include dark matter, they include the origin of the Higgs mechanism. This is how I phrase these days, the hierarchy problem, or matter-antimatter asymmetry. And these fundamental questions can be answered in Higgs physics, like in other fields of physics, but also in Higgs physics. And by the way, Higgs couplings don't really feature in this. We're going to see that in a second. What features in that argument is new particles in the Higgs engaged sector, where I like to combine Higgs and engage from my perspective, and the form of the Higgs potential that we'll come to, which we all know is our favorite question. And when you think about this, how we look for that stuff, it's not rates, it's kinematics that we're looking at. And so, or phrased in a modern way, simulation-based inference is what we are doing. We're not just measuring a bunch of cross-sections. So let me just recall, this is a slide, by the way, Georg and Sven will remember. I've been showing this slide for, I don't know, 20 years. And so it's about Higgs couplings and it's the properties of the Higgs sector. And we have the Higgs sector and the LHC is the perfect example for a physics sector where we need a global analysis, because we have tons of different channels that we can look at, production decay channels, and we have a fundamental theory, a Lagrangian, that relates those to parameters in that Lagrangian. And the question now is how do you find these parameters? And of course, the obvious thing, and the first thing you do is you just look at the Higgs couplings in the Lagrangian, and you get brilliant one results, but they're in a way answering the wrong questions, because this is not how we look for instance, for new particles, for the effects of new particles in the Higgs sector. We study the parameters, but we are not looking for the effects of new particles or new interesting physics. The way we look for interesting physics is using effective theory. So effective theory means we basically allow for new particles, and we assume that they are not kinematically affecting our observables, so that we're not hitting their mass peak. And then we are looking for their effects through high dimensional operators, in that case, dimension 6 operators. And these dimension 6 operators are listed. Some here, this is all an old story. I want to just draw attention to the first, which is the Higgs coupling, which is kind of crucial for the LHC Higgs physics. And we know this is induced coupling. And then the bottom right, you see the Higgs self-coupling. It's one of these operators. So it's just a slightly different approach, and you can write down these the prefactors of these high dimensional operators. They're called Wilson coefficients. They're called F here in my case, and then we can obviously relate them to the Higgs couplings. And you see here, for instance, that you look at GZ, the coupling ZZ Higgs couplings, and yes, you do have GZ3 is the standard Higgs coupling modification, but you have two other couplings which have a momentum dependence. And that momentum, they have a derivative, and derivatives, after I do a Fourier transform, become momentum dependence. And then you add the Yukawa structures. And then you notice at some point that if you want to describe the, say, dye boson production, so not just ZH production, but also WH production, WW production, WZ production, all of these dye boson channels, you can just add one more operator that's called the OWWW, and then you can also look for triple gauge couplings. So in the bosonic sector, you have order of magnitude 10, no, you have exactly 10 operators you can look for and that you can describe. Modulo, now we are talking about symmetries that can allow you to, so if you weaken your assumption on symmetries, you can enhance that number, but this is the minimum set. And then at some point, people tell you, I think Sally told us, for instance, that this is not all. If you want to look, for instance, for like ZH production, QQ bar prime to ZH, you have to actually consider more operators, which includes like, the modified QQ-ZH coupling, and then you end up with a fermion gauge mixing operators, and we listed some of those, and then you end up with this bigger and better basis. So this is like, the first line is essentially the old operators that we have from the Higgs sector, and then you have more of them. And they're more complicated in some way, the gauge fermion operators, because they actually link, like, properly, like different fields, like, gauge fields, Higgs fields, and fermion fields. So which also means you become sensitive to the flavor structure if you want. So now you look at them, and well, you have to answer the question like, how can I constrain these kind of parameters from rates, from kinematics, and then don't forget there's electric precision data you have to consider, because those operators we know are constrained by electric precision data. So just like, heads up to the experimentalists, like here's my favorite way to constrain those operators, and that's not from Higgs measurements, but it is from searches that include a Higgs, which are typically not part of the Higgs group because they're labeled resonance searches or like, using Higgses. And that is my favorite distribution these days, is the MVH distribution. So what people do is, for instance, Atlas and CMS both do that. You look for resonance that decays to a VH, which is typically a W prime, or Z prime particle, and that decays to a WZ on the Higgs boson. And those the searches go out to very high invariant mass of VH, and that makes them very suitable to search for new physics that is especially momentum enhanced in the tails of the distribution. Notice that when you study these kind of processes, it might well be that, like, the standard ZH star model final state is not even visible in those searches, because you're dominated by some other final states, diboson or whatever. But it's also not necessary to observe the VH final state to constrain anomalous VH events, right? You don't have to do that. You just have to be sure that you would see them if they came up. And this is like, one of these, like, results you found. This is like Anke Biekötter, and now, like, we have done this like many times. Anja Butter did it, Anke Biekötter did it, and now Emma Geoffrey is doing that, all my students. And like, you find these strong correlations between the triple gauge couplings, ZZH, for instance, induced by OW, and the actual QQ bar ZH 4-point coupling that is induced by the fermion boson operator. So that makes these searches particularly fun, also from a theoretical perspective, not from an experimental perspective. I should say, by the way, that also from a pheno perspective, these searches are great fun, because some of them are using like my favorite like tool, which is subject physics and tagging. So these are in so many ways useful, fun, and interesting searches. One operator that we tend to forget because it's a pain in the butt, but we should never forget, is the QCD operators, the triple gluon coupling, which of course affects anything you do at the LHC. Like, no matter what you do at the LHC, the triple gluon coupling operator will always, like, affect your rate or like your distributions. This is an old story, goes back to like the Simmons and Lance-Dixon's papers for the Tevatron. And of course, the same thing is true for the LHC. The good news is that, like, people have been looking for black holes at the LHC, and it turns out these like black holes, high multiplicity, very high energy searches are extremely well suited to constrain that operator. So like there's like, again, like an outside cellar data that helps us constrain Higgs physics. So it helps to look outside a little bit. And then these constraints that we see from black hole searches are so strong that we can essentially forget about the effect of this operator on Higgs searches, which is good news because it would be a pain to actually include everywhere. So, and then you do this analysis, and that's an old story here. This is our run 2 results. And then you get these uncertainty bands. And you see that the bad news is there's no anomalies. I mean, everything, like, 68, 95% confidence level, everything is like perfectly consistent with, on the left-hand side, you see dimension 6 Wilson coefficient 0, or the right-hand side, you see lambda divided by the square root of the Wilson coefficient. So the new physics scale, order of magnitude, like, what within 1 TeV, we agree with the standard model. I should say here that in this analysis, we quoted this multi-jet channel that I just showed you before. And the other thing we do is we quote FTG. And it turns out, like the really nice paper by Veronica and Sons, that this might be not quite true that this is something that we like where Higgs physics and top physics actually have to work together to get this. So we didn't actually do the combined analysis, others did. Fabio did it with friends, and like Veronica did it with friends. So we did the top sector independently, and of course now the top sector is the same story. As the Higgs sector, lots of different production channels, lots of different decay channels, lots of different operators in the Lagrangian. So let's do a global analysis of the top sector. Now here, what we did is what people should have done is we should have done for the Higgs sector as well as use next to order predictions, theory, and certainties, by the way, not only from scale variations, because those might be really, really small. So if you calculate next to order, you'll find that you might want to think about these uncertainties from scale dependence for electrolytic processes. Again, something you all know for a long time. And then you look at the kinematic distributions. Here's there's only one thing I want to say, and that is if you look at the top groups, there's a strong tradition in the top groups, Atlas and CMS, to unfold kinematic distributions like the invariant mass of the TT bar or PT of the top. This is extremely useful for this kind of global analysis, makes it much easier for us to apply and include these kind of observables in our kinematic analysis, because we can actually now, without having to second guess stuff, we can go into kinematic tails and look for our favorite effects in these kinematic tails. The specific problem of the top sector is that we have a lot of different flavor structures of and in general, structures of for fermion operators, and you have to try to disentangle them or not. So it's actually funny. So if you look into the details, you find that in the Higgs sector, flat directions are usually lines that extend to whatever, to infinity, very far out, and they ruin your analysis. It's interesting, the four fermion interactions, the technical complication of flat directions is that they're circular. So instead of actually getting the width of your ring, you actually get the radius of your ring as the constraint, which is weaker, but it's at least, unlike in Higgs, exists. The bad news is there's still no anomalies in the top sector. And here, I just put S-fitter, Higgs and top global analysis side by side. To the left, you see the Higgs sector, the gauge sector, including electric precision data. To the right, you see the top sector. And as I said, other groups have combined those two in one analysis. I should say, I would have thought that originally I would have thought that the two of them are relatively separate, naturally separate. TT bar Higgs essentially constrains the Higgs sector, and TT bar constrains the top sector. But as I said, it turns out Veronica has this really nice result that TG is actually one of the operators that these two analyses actually talk to each other. So these are very nice results. The only question that we have to ask us is that what we want to do? I mean, is that the future? Or to be a little bit more modest, is that analysis giving me the answers to the questions I want to ask to particle physics? Okay, so the answer is obviously I wouldn't bring it up. This is Hinchcliffe's rule, right? The answer is no. Because I'm interested in new physics and new particles. I mean, I think it's fine to actually integrate them out and get an EFT and search for effects of new particles in an EFT, but that still means I don't really care about Wilson coefficients. I care about the new particles inducing non-zero Wilson coefficients. So what we did recently with a bunch of people here in Heidelberg and in Aachen and in Siegen and in Würzburg now is ask the question, so okay, now when I do that, I do an EFT analysis and I want to interpret this in terms of a model. So what happens? And then the model that we take is my favorite model, where you actually find effects in an EFT analysis, with the triplet benchmark model that everybody uses. And there's two questions we want to ask. First of all, because we're Germans, we ask the question, what's the effect of going from tree-level matching to one-loop matching? And the second thing is, now that we go to one-loop matching, there's a new scale. There's a matching scale that's involved in matching those theories. Namely, the question: where do I match these two theories? Roughly at the mass of the heavy particle, but roughly doesn't mean with a factor of 2. So now what we have is we have just the way we have the factorization and renormalization scale and perturbative QCD. In this perturbative matching, we have a matching scale that we have to consider. And many people have heard me say that I don't care about consistency of EFTs and how actually describes for none of this when I do it in EFT analysis. That I do at I take dimension 6 Lagrangian dimension 6 Lagrangian face value and do the analysis. But if I do that, I have to actually, when I match stuff, I have to reconsider these kind of uncertainties, and that's among other things that matching scale. So this is our paper. I should say that matching scale theory uncertainty was first mentioned in Higgs physics, I believe, by Sally and collaborators for Higgs for the Higgs portal model. The only problem is that there it had a very small numerical effect, and we were a little bit more lucky or unlucky. Well, it depends how you. Well, we were lucky enough to find larger effects. So here to the left, you find the relation between GH twiddle, which is one of these parameters that you see defined up there, and FB, which is one of the Wilson coefficients in the language which you use to do our global fit. And you see that for a smaller matching scale of 2.5 TeV roughly, this dependence flattens. So you lose sensitivity to GH twiddle. And when you now allow for your fit to vary over this matching scale, because that's what you do with scales. You vary the scales and then you do a profiling over the scales technically in the fit. You will find here in the central panel, you see that the GH twiddle limits weaken significantly. So without varying the matching scale, like without Q of, you just fix it at say 3 TeV, you see that you get this very narrow band. And then you have the fleur-de-lis come up when you actually go to smaller scales. And then you, when what you do is you profile over that scale and you get the bigger limit. And the bigger limit is a worse limit. Okay, so EFT uncertainties like that should be part, like, these uncertainties should be part of the matching and then matter a lot. By the way, just something I don't want to talk to a lot about is that we also checked, like, how good are the limits that we get when we put limits on that triplet vector triplet model through a SMEFT analysis or directly, and we find that the SMEFT limits in the small regions of parameter space, where both of them actually are technically applicable, the SMEFT limits are significantly weaker. So experimentalists, please keep looking for full models, because SMEFT limits are weaker. And there's simple reasons for that. For instance, well, SMEFT ignores the higher dimensional effects, dimension 8. So if things get real big, dimension 8 is going to be big, which means and they are ignored and our limits get weaker. It's a very simple explanation for that. Okay, if you want to look for kinematics, here comes my little technical thing, and everybody who knows me knows that my favorite little technical hobbies. And for a while, one of my technical hobbies has been information geometry for the LHC. So essentially, when we look at this analysis I showed you a minute ago, we have turned the main LHC questions from comparing two hypotheses, which means here's signal, here's background, to continuous measurement. So how well can I measure a certain Wilson coefficient, say, right? In an EFT analysis, and technically that means that we move away from the likelihood limits, Neiman-Pearson likelihood limits, to something new, and that is information geometry. And it's in a nutshell, it's very simple. What I want is a covariance matrix now. I want some kind of a measurement error in model space. Model space is G, right? And it's defined just the usual way that any covariance matrix or in any uncertainty in model space would look. But I can calculate it. What I calculate is the Fisher information, which is just the likelihood double derivative with respect to model space. I can calculate that from Monte Carlo very simply. And even better, I can integrate over phase space. So when I do a log likelihood, then I can actually just add this Fisher information for different phase space values. And then the Cramer-Rao bound comes in and says, well, that's great, because I can actually apply get a limit on the covariance matrix, and that's on my measurement error from the inverse Fisher information, which I can calculate. So this is just in one line, this simple math. What this allows me to do is I can compute the available information, the maximum available information from certain phase space regions. And I can, for instance, ask the question, how much information about a certain Wilson coefficient is in LHC channels, measurements, phase space, what happens if I apply certain cuts, what happens if I add another channel? I can ask these questions. I can do this, including CP violation. We wrote all these papers, so I don't want to show them here, but this is technically something we can do. So what I'm saying is, go back to my first slide, information on kinematics is something that we don't only use, as I showed you, but something that we actually control. Now, here's a nice little new development that's by Johann Bremer, Felix Kling, and Karl Kramer, and that is moving that information geometry analysis to the detector level. So we know that, for instance, when I look for Z2 neutrinos, I only know something about the transverse information, or Higgs to BB bar is like hugely split out in phase space. So like, or like backgrounds have different final states where I have to integrate out over like, another particle in the final state. And then this standard information geometry picture doesn't apply because it assumes that I have the same final states for signal and background. So what I now want to do is I want to like do my likelihood ratio at the detector level. So like, this is like the definition here, log of P xd is the detector level. And it involves an integral in the numerator and in the denominator, and that means I can solve it. If it was an integral over both, like over the log of the ratio, it will be fine, but it's different integrals. And here comes in a great trick. And you can turn that question, that extraction of the detector level likelihood, into a minimization problem by writing down that function that I just wrote down, fxd, and there's an integral over xp, and then it's like, this thing in parentheses squared times probabilities. And I can actually, I can minimize that. I can minimize anything, right? I mean, like this machine learning comes in with minimization. And it turns out if I define my G function here in this minimization problem as the ratio of the pattern level likelihoods, then my result for the detector level likelihoods is going to be exactly that G hat of xd, which I can extract numerically implicitly when I minimize this function capital F. That's called the likelihood ratio trick, I believe, and it allows us to do a whole lot more with kinematic information. So like, we can't only do this at pattern level, we can also do this at detector level. One thing we can do is we can benchmark stuff. And here's just one example. We did this with, like, again, with Johann and with Sally and Sam Hommeler, great student, and Felix Kling. So what we found, what we looked for is the best analysis for VH production for a bunch of operators. Just pick some. And like we picked those 3 operators because they affect the kinematics and they affect the kinematics in different ways. And then we included backgrounds and detectors. So we use MadMiner if you want. And then we asked the question, like, what about, like, my favorite 2-dimensional observables, PTW versus MT total, for instance, versus simplified template cross-sections as implemented in Atlas and CMS versus the full kinematics, which I can define through my information geometry. And what we find here is, just take one of the points here, like, sometimes you're lucky, the left-hand point, HD versus HQ, and you find that, okay, the 2-dimensional distribution, simplified template cross-section, an improved version of, like, adding more information to the template cross-section is all the same, except that it's not exactly the full kinematic information, which is the blue one. And then on the right-hand side, for instance, when you look at, like, the squared operators, you see that when you look that using the standard simplified template cross-section is actually the biggest the ellipse. You can see that I can get more information out of that by approximating the 2-dimensional distributions through, like, an improved set of simplified template cross-sections, including here the transverse total transverse mass and the PT of the W. And then you get, like, you approximate the full information better. Not quite perfect, so we are not saying that this is the final answer. It's not. Like, we need to do more. And Sabine Kramel just, like, published a nice thing about, like, like publishing the likelihoods, but still kinematic information means we should go to these modern simulations tools and we should use them to do this kind of answer these kind of questions, because we can obtain well-defined answers for them. So I also promised to talk a little bit about Higgs self-coupling in exactly that view, kinematics, like, proper testing of hypothesis EFT. Well, EFT I don't have to do because EFT already wrote down the operator that, like, does it all. So that's just the triple, the phi cubed operator here. Now, let's just remind ourselves, why do I look for the Higgs self-coupling? I mean, the Higgs self-coupling, I can say I'm looking for that because it's just the one remaining parameter in the Standard Model. But you know what? I really don't care. Why should I look for the next parameter, like, of the Standard Model? I mean, like, is there anything more to it? And the answer is there's tons more to it, and that has to do with baryogenesis. So just a reminder, baryogenesis, to get baryogenesis, you need to fulfill the 3 Sakharov conditions. One is baryon number violation, is something I'm not going to talk about here. Second one is CP violation. CP violation we know already is something that we can not only, like, generate through the Higgs sector, but we can also measure it at the LHC. And then a departure from thermal equilibrium, it's called or the first order electroweak phase transition. And there's, like, an old classic paper by Jim Wells, Christophe Grosjean, and Géraldine Servon, where they show that you can achieve strong first order phase transition through dimension 6 Higgs potential operator. We look for this, by the way, to see if that has something to do with the dimension 6 nature or the specific nature of the potential. It turns out we tried a bunch of different potentials here, like log potentials, exponential, weirdo potentials. And what we always find is that the answer for the EFT result, like, that goes back to Christophe, Geraldine, and James, is still true. Like, so if you want to have a strong first order phase transition here, what you see is this on the vertical line is the Higgs self-coupling modification, and what you want is you want to go from red to the blue. You see that, like, you get a strong first order phase transition if the Higgs self-coupling changes by something like 50% to 100%. So it gives a significant change in the Higgs self-coupling, the physically observed Higgs self-couplings based on whatever potential models you're looking for, you will always get that relation. Okay, so we can look for that. How do we look for Higgs pairs? That's also like a reminder. That's an old story, like, because that goes back to 88. Nigel and Jochen van der Weijt found out that you can actually look for the Higgs self-coupling in Higgs pair production. Well, I mean, they showed how to calculate Higgs pair production, and there's a famous paper by Maggie and friends where you see that you look for Higgs self-coupling modifications, glue to HH. The arrow down means you look for them by searching for a lack of events. So if the self-coupling goes up, your number of events overall goes down. This is what, like, in that curve, what you see here and observed in last century sometime. And then it's a 2-to-2 process, so it's not that hard, right? So what you have is you have an approximate threshold cancellation at for MMH roughly at 2 mH. You have an absorptive kink at MMH roughly at twice the top mass, and you have a triangle suppression in the high invariant mass tail. And you can do look at these, like, effects. And here's a, like, plot by Gudrun Heinrich, for instance. She said, like, you can do these kind of things. The only thing is the threshold cancellation when you go to next to leading order is actually not exact, because the top mass, the large top mass approximation for the kinematic, not for the total rate. For the total rate, it's fine, but for the kinematic of diHiggs production is very bad. And that, like, she's done some beautiful work on that. The statistical limitations of this is the Higgs pair production searches are, or, like, searches for modified Higgs self-coupling are totally obvious, right? Like, it's just not a lot of events to deal with. So this is obviously calling for some global EFT or model analysis. And this is just a paper by Christophe, which I'm quoting, where they combine all kinds of single Higgs and double Higgs channels to search for the Higgs self-coupling. Please note, though, whenever you do this kind of combined analysis, right, you have to be very clear what are my assumption, what's going into the analysis. But a global analysis, like, what are the operators I'm considering, what are the measurements I'm considering, what are the symmetries I'm assuming, all this, etc., etc. Okay, but if you do this, like, right, you might be able to, like, look the Higgs self-coupling here. And the one thing that I'm going to show you here is, like, the curve. This is an old paper, like, with Tao Han. Look at the 14 TeV curves and, like, the measurement of the Higgs self-coupling. And what we see is that, like, the blue curve, the black curve, you see that, like, you can reach, like, whatever, like, order of magnitude modifications. I'm getting to my end, don't worry. So now, last question. I told you, like, first order phase transition. What about CP violation? Well, CP violation is something that is very well established. And as I said, ask Maggie Mühlleitner about it. Here's just an example. You can, like, have CP violation in the MSSM or the NMSSM. And you can induce that through, like, a phase, essentially, in one of the Higgs doublets, or a complex singlet, and then you get a complex Higgs potential. It's important, so you can induce it through the Higgs potential. Then the Higgs interaction states mix, you break CP that way, a complex top mass, essentially. And then you can compute the Baryon symmetry. It's actually all computable. Everything, like, you can do from then on, if you have a well-defined model in the Higgs sector, you can actually go and you can compute the, like, baryogenesis, like, or, like, here, the Baryon symmetry. Eta over eta over eta and observed, and you can see, like, what you get. Okay, so, like, you can calculate that, and you can search for these new particles that you need for electroweak baryogenesis, and you can search for CP violation. Another way, like, you can do that is just another example I want to show you. If you don't want to modify the Higgs potential, you can also modify in the 2Higgs doublet model the Higgs Yukawa couplings directly, and you can, for instance, take, like, an off-diagonal entry in the Yukawa matrix that you can make that complex, and then you can search for that in new channels like, VH plus production.
Tilman, you seem to be muted.
I wasn't even muted, I was removed from this conference.
Okay.
Probably by somebody with excellent taste in physics. So here we go. So that's my outlook. I will ask to be fast to allow time for questions. So first of all, I think that she has the best data sets for decades to come. And like one of my other hobbies is like, it's time to for steps in modern data analysis, and they're overdue. Rate measurements, I know we need to show them, but really from my fundamental physics perspective, they're fairly uninteresting because, you wouldn't even have found the bloody Higgs in a rate measurement, right? Remember that. Measurements of fundamental parameters are much better, couplings. But really what I want to do is I want to turn these fundamental parameters into something like effective operators where I can actually look at the effect, how they relate to BSM physics. And then of course, at the end of the day, we want to find some real interesting BSM discovery at the LHC, which might be in the EFT framework because we can actually produce a number of these new particles on shell, or it might be a direct search, or whatever it is. Future Higgs physics, like as particle physics, let's not forget that we do Higgs physics for a reason, and that is not to get to know the Higgs potential a little bit better, right? I don't care. So we do that because there's a link of Higgs physics to dark matter, and there's a link of Higgs physics to baryogenesis. Baryogenesis is especially interesting because it's really hard to actually look for baryogenesis in other channels at the LHC. So what we need to do is we need to search for extended Higgs sectors. Again, Higgs pair production, EFT searches, direct searches, right? All of them have to be done. And if you look for fundamental physics impact, you want to look for symmetries because everybody knows dark matter means a symmetry, some kind of a Z2 symmetry. Baryogenesis means CP symmetry. So we have to look for these fundamental questions in the Higgs sector. And yeah, that's my theory rambling. Thank you very much. Thank you again for inviting me. As I said, it's a pity we can't be there and fight in person now, but yeah, shoot.
Thank you, Tilman. Most enlightening talk. Yeah, I feel useless, to tell you the truth. So, okay. So the floor is open. I don't see any hands.
Oh, I see a hand.
There's a hand. Okay.
The hand.
Jörg, please go ahead.
He's muted.
Yeah, I tried several times to unmute. It seems to have worked now.
Yes.
So yeah, so in order to get things going, let me start with some provocative or one provocative question, and I hope Tilman you will not mind. So what you told us, I mean, we had these discussions at the LHC Higgs physics for many years. How should we do this? How should experimental data be analyzed? And many of my theory colleagues, including you, told our experimental friends from Atlas and CMS the mantra: what you have to do is to implement these SMEFT analyses with the effective operators, and you have to go through these many operators and set up this framework. And many person years, both in Atlas and CMS, were spent on this. And I was always very rather skeptical on this from the beginning, whether the effort that goes in would really be worth the outcome. But now finally, after all these years of efforts, you tell the experimentalist, look, if you want to set a really sensitive limit, better go to a model directly rather than via the effective field theory result. Well, we could have anticipated this outcome from the start. It was always clear that going to a specific model will make things much easier, and you will also get the full information. So the limits will be more sensitive. So with this in mind, so what is your take on all this huge machinery that has been built up now?
Yeah. No. Okay. So first of all, yeah, Georg, maybe I should just admit that like I'm coming to like an age like yours, and like, you know, the voice of like wisdom are like is hitting me. But no, that's actually not. So if you don't have enough energy to produce the particle on its mass shell, right, you need an EFT. And so what we find is that if you look at like, you know, like a particle, the range where like, you know, you can produce the particle on shell and you're safe, then the direct searches will work much better. And there's a transition region, like, you know, where both of them might be applicable. And then if the particle gets heavier, you can't produce it at the LHC, then you need to use the EFT. So what we are talking about now is essentially, I'm joining you in the sense, I think EFT is our standard framework, and it's a great limit setting framework because it actually allows us to systematically study lots of different kinematic distributions, and we do that, and that works great. And we have to continue doing that because to me, it's the best way of systematically looking through kinematics to search for stuff. However, we shouldn't forget that if we have a full model in mind, right, we should also do the analyses for the full model and keep doing the analysis for the full model, because the EFT will always be an approximation to it numerically. So I think, Georg, I'm thinking of myself now entering like more like a precision kind of era where I care about the details of the, like, you know, the outcome of the analysis. So the bottom line is, for the best limits on the model is very hard to beat. On the other hand, for systematically searching in kinematics, and that's really close to my heart, you have to use the EFTs. Is that a fair agreement, Georg? You can go and have beer on that?
Yes. But just to say, I mean, the impression that was given by some theorists, probably not you, but by some theorists to the Atlas and CMS experimental collaboration at the beginning was, if you do this effective field theory implementation, you will never in your life have to talk about any specific model. You can abandon specific models in this way completely. And I think this was not true from the beginning, and we see it now that this is not the case. But we can certainly agree on what you say.
I totally agree with you, Georg. And the other thing I should say that I emphasize that my favorite EFT input data comes actually from new physics searches, right? So I think these things are really much more intertwined than, like, you know, than it's maybe appreciated. But, like, you know, I've always been of the view that the like direct search channels were my favorite input to my EFT analysis. So they can't be separated, I think.
Excellent. So with this, I think we are ready to go on to Richard, who was next.
Yes, hello. I very much enjoyed the question of Georg. This is exactly my point of view. But we missed one of your slides because we were interrupted. And one of your slides was about baryogenesis, where you had apparently quoted some allowed masses for the Higgses. And this goes exactly in the line that we are discussing. These masses are relatively modest, right? When you say 300 GeV, 600 GeV, if I read well your slides, one has to search very badly because baryogenesis, as you say, is really a must for us. So how do you reconcile, I mean, this running to very high masses in the spirit of your approach, and the explicit models which tell you that you have indeed to search for light Higgses?
Yeah,
I call light with below 1 TeV.
Yeah, I know. Yeah, it's a thing. That's my light as well. So there's two things to remember when you look at, like, you know, when you look for baryogenesis. And I think the Higgs sector has a great opportunity of doing that, right? There's two things you're looking for. One is CP violation, which, by the way, also has something to do with the way we set up our EFT, right? Because you set up an EFT after assuming symmetries, not the other way around. So that's the first thing. So like, you have to think about your symmetries before you set up your EFT. And that means you have to set up your EFT with deciding ahead of time if you want to look for CP evaluation of aberragenesis. And the second thing is the departure from thermal equilibrium. And here, the first part I showed you is there's this famous paper, and it's like I really love this paper. This is why we expanded on it. Is you can do this the thermal equilibrium. You can do that using an EFT, but at the bottom of the BFT, there's always some kind of new physics you have integrated out, right? And here for the LHC, of course, like if you ever find something like this, I want to see the real particle. I don't want to be stuck with EFT effects. So we're thinking about what if you extend the Higgs sector to allow for electric baryogenesis. We can describe this through an effective operator, but we should always, as particle theorists, we should also always keep in mind that thing has to come from somewhere. An effective operator doesn't come out of nowhere, right? I mean, it comes from integrating out something. And these particles, and now you're looking at 1 TeV, by the way, but then now you look at my EFT analyses, the results. Where are they? Here. And you see, 1 TeV is about it, right? It's all totally consistent, right? This is what we should be looking for and what we are looking for. And you have to always keep in mind that for fundamental questions, we want both answers, if we can have them.
Yeah, and for the record, let me add that experimentalists would also like to see the real particle, the real new particle.
Yes, I have no doubt.
We don't
they should be encouraged.
Nicholas, Nick Wardle.
Yeah, thanks a lot for the talk, Tilman. So my question was a little bit related to what Georg had asked as well, and putting aside direct searches, where I think we all agree with, we really want to see the things as well. So thinking about the EFT analysis and as a theorist, the inputs that you want for this analysis, is it worth the experiments spending more time in developing analyses that are really targeting certain EFT operators? I mean, thinking about your slide that you had about the Kramer-Rao band, or does it make more sense to really just push in the direction of differential measurements of diboson processes, Higgs processes, that kind of thing, and then use them as inputs to a global EFT?
Yeah, that's a very good question. So the way I'm concerned, the way I think about it is, I don't know a single search that I would want you to do that would add something to my global analysis and that you're not doing. So I think all the searches that I would ever want are being done because it's extremely complete, right? I mean, even in TT bar Z, TT bar W, single top, this is all being done, right? I have absolutely no complaint in the searches you guys are doing. So that would be fine. The important thing is oftentimes it might the way these searches are reported make it easier or harder for us to interpret them as part of a global analysis. So there, I think the top group is doing a marvelous job with or as long as they will do with the unfolding, right, to MTT and PTT. And I think here for the Higgs group, you guys could make life a little bit easier for us. And you see, take the simplified template cross-section, right? They're defined within the Higgs group, and that's fine, right? However, I'm showing you here my favorite analysis is not in the Higgs group, right? And it's an exotic search. And it is nothing but MVH at very high momentum throughput. So I think I have no complaint about the searches you're doing, but I think sometimes it would be easier to make these searches available to us for the global analysis, provided that we still do the global analysis a couple of years from now, which I'm not even sure if Atlas and CMS might not just take over there. But Nick, I'm fine. I can't tell you a search that I want done and that you're not doing. It's just about how to publish and present the results.
Yeah, I think that's also what my question was about, in that in some sense we can also put the interpretation on top, whether it be for a direct model, a specific model or an EFT. But if you're saying that really the thing that you take at the end of the day is, this plot here or this data here, then of course making that well, publishing that information is maybe more important for your fits. Okay.
Yeah, from a technical perspective, I would say, like, well, this is just my personal opinion. I think if you look into modern, like, machine learning kind of stuff, I think where machine learning can have the biggest impact is that it actually makes unfolding much easier, because I know how hard it is normally, right? And my hope is that we can make progress technically to unfold more. And unfolding, to me, of kinematic distributions, 1 2-dimensional kinematic distributions, I know it's extremely hard. It's very hard to control, but I think this is would be my favorite goal.
Okay. In the remaining time, first of all, next in line for questions comes from the chat. Actually, it's from Sven. What is Sven Heinemeyer? What is the minimum mass of a new Higgs so that the EFT is still valid?
Sven, but it depends if you have a channel to produce in the S channel, right? I don't think there's an answer, but I mean, it depends on the analysis you're taking into account. I mean, I would argue that the EFT is valid until I have a channel where I see the mass peak, and then the EFT is dead in my data. And I'm not. And that depends, right? I mean, might be because, like, something appears in the T channel, right? I mean, T channel is fine. You can describe that through an EFT. So, and it's analysis dependent, right? I mean, some particles, if you could in principle observe them in the S channel, but unfortunately it's in a final state, like bloody jetty final state that you never see, you'll be safe, because, it has a mass peak, which is totally accessible to the LHC, but you never see it, right? It's fine. So I don't think there's, I would argue it's a question that depends on the analyses. It's not a global question you can just answer.
Okay, great. There was a raised hand, but then it disappeared.
Tanya.
Yeah, but perhaps it was already addressed. Georg has one more, and Tanya is back. So shall we go back to Tanya first? Tanya, you have the floor. Virtual floor.
I think she disconnected.
Yeah, she just disconnected. So Georg, final.
No, sorry. Somehow I couldn't unmute, but now I can unmute. So just a brief comment. Can you hear me?
Yes, we can hear you very.
Just a brief comment. So along this discussion of EFT versus concrete models, I mean, my understanding was from Nicolas' question or comment, it's also a manpower discussion, right? I mean, in an ideal world, we measure everything. Each specific operator has a dedicated search. Each new physics model in each channel has a dedicated search, and so on. And this would be fantastic, but it's not possible. So I just wanted to comment. I think there are still many concrete model channels which are not investigated at the moment by the LHC experiments. Yeah, and then it depends on which model you're interested in, and you can have a long debate whether that's a good model or not, and so on and so forth. But just, and I also didn't try for each of these models to see whether I couldn't fit it now to or map it to some EFT analysis. But I mean, as Sven also, I think, pointed out, there are also many models with light scalars or light new particles, which might not be covered by these searches. And first comparisons have been done by the Brookhaven group to see how this matches or not, but one shouldn't forget this. Okay, it was more a comment, and this is why I also de-raised my hand, because I'm not sure how important it is, but just from another theory perspective, I would say, in addition into the discussion. Okay.
Yeah. Going to wrap up my talk?
Yeah, Georg, you have the final word before we move on to our young scientist forum.
Yeah, I just wanted to briefly come back to Sven's question. I mean, Tilman, when you see a mass peak, then the EFT is obviously no longer valid. But I think Sven's question was also more like the range of validity in the sense of for up to which scale can you neglect dimension 8 operators in comparison to dimension 6 and things like that. And there you will be restricted even before you go to the mass peak. So I guess Sven's question was more along those lines.
Yeah, I think that is something that is correct. I think so even if you cannot see the P itself, I mean, yeah, I think it really depends on the observable. Exactly. There might be observables where you, in spite of the fact that you cannot see the actual peak, you will still become very, very sensitive to dimension 8. And that would be, I mean, then your dimension 6 outcome will not be a very precise result, right? I mean, this is like, you know, what this matching comes. But sometimes you might also be lucky in the T channel, right? And I mean, the effect is not that big. There's also symmetries. I should say, by the way, there's like good reasons to do dimension 8 because do you want to do quartic couplings, gauge couplings and stuff, right? I mean, so you will never hear from me that it makes no sense to look at dimension 8. Yeah, I mean, but I'm saying is there is no rule. It's an observable dependent rule. That's what I want to say.
Okay, thank you.